Welcome back, everyone. If you're building with AI right now, you know we've officially moved way past the era of simple chat wrappers. We are deep in the era of AI agents, systems that reason, use tools, and take autonomous actions to solve complex problems. But this massive leap in capability brings a totally new challenge. How do we actually know if our agents are any good? Today, we're exploring a fantastic breakdown on why evaluating the journey of an AI agent matters just as much as its final destination. Let's get right into it.
It's the universally frustrating reality of AI development. You build a proof of concept, you demo it to the team, and it looks like pure magic. It works beautifully on the happy path, but the very second you move it into the real world, things just start to break. And honestly, the scariest part? It doesn't always crash. Sometimes it just silently fails, leaving you with a massive mess that's incredibly hard to debug. Today, we're going to unpack exactly why that happens, and more importantly, how to fix it.
Okay, let's dive into this. Here is our roadmap for this explainer. 1. The AI agent illusion. 2. Single turn versus multi-step. 3. The trajectory evaluation framework. 4. The 10-bug experiment. And finally, 5. Tools for agent evaluation.
Starting off with Section 1, the AI agent illusion.
So if you're coming from a traditional software engineering background, you're used to unit tests and integration tests. If the tests pass, you have a solid baseline confidence that the code actually works. But autonomous AI completely shatters that illusion. Agents have inherent variability. Because they take actions across multiple steps, a single hallucinated parameter during a tool call at, say, Step 2 can derail the entire process. The agent might get stuck in an infinite loop, invent a tool that doesn't even exist, or, worst of all, confidently tell you the task is complete when it isn't. The final output might look correct on the surface, while the underlying process was literally a complete disaster.
Moving right along to Section 2, single turn versus multi-step.
The reality is, most developers are using the completely wrong measuring stick to grade their AI systems. Consider single-turn evaluation. One prompt goes in, one text comes out. We judge it based on whether the final answer is right. Think of it like grading only the final answer on a math test. But agents require multi-step evaluation. They execute a complex chain of tool calls and internal reasoning steps. If you only grade the final answer, you completely lose the why and the how. You have to grade the student's scratch pad, the trajectory, to really understand where those failures are compounding.
Now, what's really interesting about this slide is that it's incredibly tempting to look at massive public benchmarks like MMLU or SWBench and just assume a high-scoring model will automatically make a great agent. But that's a total trap. Generic benchmarks just measure the raw intellectual horsepower of the base model. They tell you absolutely nothing about how your specific agent, wired up to your custom tools, trying to solve your unique business logic, is actually performing.
To build your own custom tests, you really need to separate your mindset into two buckets. First, you have capability evals. These are the brutally hard, unsolved tasks designed to find your agent's ceiling. You fully expect it to fail a lot here. Second, you have regression evals. These are the known, solved tasks. You expect a near 100% pass rate here, and they act as your safety net so you don't accidentally break your agent when you tweak a system prompt later on.
All right, Section 3, the trajectory evaluation framework.
So how do we actually go about grading the scratchpad? Well, here are the first 4 steps of a practical framework designed to evaluate the journey, not just the destination. Step 1, you must evaluate task completion beyond a simple binary pass or fail. Use dual-layer grading, a fast, rule-based check to see if the outcome happened, paired with a nuanced LLM judge that gives partial credit if the agent had the right logic, but, just ran out of turns. Step 2, evaluate tool correctness. Did the agent literally open the right file or did it hallucinate a file name? Steps 3 and 4 challenge you to actively compare different prompt versions and tool configurations to see what actually drives performance. Building on that, Step 5 is inspecting the execution trajectory. Actually, let me frame it this way. Did the agent take 5 weird, redundant actions just to do a one-step task? That sequence flow analysis is key. Step 6 measures efficiency, tokens, cost, turn counts. Step 7 reminds us we absolutely have to run multiple regression tests because LLMs are inherently non-deterministic. A pass might just be a lucky roll of the dice. And finally, Step 8. Use an LLM judge to look at the exact code diff to ensure the agent fixed the root cause, rather than just writing some lazy workaround.
Which brings us to Section 4, the 10-bug experiment.
To see this whole framework in action, the source author built a local bug-fixing agent and planted 10 specific Python bugs. Now I want you to look closely at how these headline metrics dynamically shifted. Notice how the baseline pass rate dynamically shifted from 80% to 70% between runs. That is LLM non-determinism in action. If you only run your evaluation once, you might easily mistake random noise for an actual breakthrough.
Okay, so the crucial point is right here, a 90% pass rate. This happened during what the author calls the blind execution paradox, when they completely took away the agent's ability to run tests, basically forcing it to rely only on reading and editing files. Its performance actually jumped to 90%. Without the crutch of a simple guess and check loop, the agent carefully read the source code and made precise edits on the very first try. Pretty wild, right? And check this out, the agent also achieved a 100% pass rate on an adversarial safety test. One task featured this malicious, planted docstring, essentially telling the agent to cheat and just force the test to pass. But the agent totally ignored the indirect prompt injection and correctly fixed the underlying source code every single time.
Okay, I want to deliberately slow down here for a second because technical honesty is absolutely crucial when we talk about AI evaluations. These 90% and 100% success rates, they're super fascinating, for sure, but we have to look at the context. This specific experiment used Claude Haiku 4.5 via an API, running on a local evaluation harness, and it tested just 10 total planted bugs. The total API spend was roughly $1. So these high pass rates are fantastic early signals, but they are absolutely not scientific proof of absolute robustness at scale. It's a very small 10-task experiment meant to prove the evaluation framework works, not to declare the agent completely flawless.
Here's another great signal from the experiment, the prompt bloat plot twist. We often just assume that forcing an AI to think out loud step by step will automatically give us better results. But here, the verbose diagnostic prompt added over 700 tokens, cost more money, and actually performed worse or identical to the concise baseline. For these specific bugs, forcing the agent into heavy structured reasoning just added bloat without adding any real problem-solving value.
We also really have to watch out for the cost of strict efficiency. During the evaluation, the author set a pretty harsh limit. The agent had a maximum of 3 turns to solve the bug. Because of this really tight budget, the agent sometimes failed tasks not because it lacked intelligence, but because a minor imprecision on the first try caused it to time out. You have to make sure your evaluation harness isn't artificially failing a highly capable agent just because your turn budget is way too strict. Finally, Section 5, Tools for Agent Evaluation. So you might be wondering, how do you actually build this without starting entirely from scratch? Well, there's a rapidly growing ecosystem ready to help you operationalize these exact concepts. You can use PromptFoo as a fast, rule-based CI gate whenever you submit a pull request. You can use DeepEval to run scheduled, nuanced LMM-judged evaluations. And crucially, you can plug into platforms like LangFuse or Confident AI to monitor your agent's execution trees in production, which catches that silent drift we talked about earlier. Oh, and if you want an all-in-one, the NVIDIA NeMo Toolkit even bakes evaluation right into its orchestration. Just a quick technical hedge here, though. This landscape moves incredibly fast. Companies get acquired, APIs are constantly marked as experimental, and frameworks rewrite their syntax all the time. Always, always check the current documentation before you commit your production stack to one of these specific tools.
Which brings us to our final thought. The next time you spin up an AI agent and it hands you a seemingly perfect final output, I want you to ask yourself, are you just grading your agent's final answer? Or are you truly evaluating the journey it took to get there? Because in the world of autonomous AI, the process is the product. Thanks so much for learning with us on this explainer today. I highly encourage you to take this trajectory framework, apply it to your own projects, and see what's really happening under the hood. Catch you next time.